As remote as it may be, the possibility is always there. An aborted takeoff at or near V1. It happened to the crew of this DC-10 on takeoff from JFK. Little did the cameraman in the cockpit know that he'd be recording anything other than a normal takeoff. But just before V1, birds were ingested into an engine. Immediately, the pilot initiated a high-energy abort. The aircraft stopped, but off the runway. Although all on board escaped serious injury, the aircraft was destroyed.
It's often been said that pilots are the only people in a company to make multi-million-dollar decisions in a split second. Certainly a problem before V1 demands an immediate decision and action. Do you stop, or do you continue to take off? That question is perhaps one of the most crucial any pilot will ever have to face.
Pilots are taught that if they lose an engine before V1, it is legitimate to abort the takeoff. But they may not have been taught what to do about a failure of a nose gear tire tread, a warning light, or a blown tire.
In the next few minutes, we'd like to offer you some food for thought in an area in which there are very few absolutes. This information is designed to help you make that multi-million-dollar decision.
You're accelerating down the runway with 270 passengers and an aircraft that weighs 480,000 pounds. You're approaching V1. Suddenly you feel a bang and a vibration. What do you do? To help you make your decision, let's look at the ramifications of some past rejected takeoffs. The pilot of this DC-10 aborted the takeoff when he got false/disagree light and takeoff warning. The aircraft was damaged beyond economical repair. The pilot of this DC-10 rejected the takeoff when he lost 4 tires. The aircraft was a total loss. The bottom line? A rejected takeoff at or near V1 is not without ramifications. A high-energy abort often results in considerable damage or loss of the aircraft.
Note that these incidents did not involve engine failure. We've already indicated that aborting for engine failure before V1 is legitimate. But it makes little sense to abort when you suspect a problem with the braking or the tires. First of all, you've already lost some of your stopping capability. Secondly, why risk an abort if you can fly? The only high-speed tire problem worth a rejected takeoff is one that has also caused serious engine or flight control damage. Even though the possibility of a rejected takeoff resulting in serious accident is highly unlikely, about 1 in 6 million, it brings to mind an old saying: those who don't learn from history are destined to repeat it. This statement is particularly relevant when we look at the statistics for jet transport RTOs initiated at or above V1.
Since 1961, there have been 33 jet transport RTOs reported in the free world that resulted in fatalities or destruction of the aircraft, or both. 7 of the RTOs were due to catastrophic engine failures or control problems initiated below V1. These aborts were legitimate, but 24 of the remaining 26 total loss or fatal RTOs were either initiated above V1 and or were associated with tire failures. So perhaps we've started to answer the question, what do you do if you feel a bang and a vibration? In most of the past cases, it would have been much better to continue the takeoff. Many problems, such as a false warning or tire failure, can be sorted out in the air. You're approaching V1 with 300 passengers in a 460,000-pound airplane. Suddenly you experience an engine failure. What do? All regulations tell you to abort because you do not have enough speed to continue the takeoff. In the next split second, you will begin one of the most demanding maneuvers a flight crew can perform, especially if initiated at or near V1 in a runway-limited situation.
This motion-based simulator at McDonnell Douglas is used in testing pilot reactions and making high-energy abort maneuvers.
Both experience and the RTO simulation program have shown that pilots must recognize and plan for the possibility of a rejected takeoff. The simulations make it crystal clear. A pilot must be mentally prepared to stop during acceleration to V1 and have knowledge of the runway condition and his aircraft performance. As you know, one of the most critical factors affecting a takeoff is the V1 speed. V1 can be thought of as a speed associated with the distance along the runway. But V1 is something more than a decision speed. It's more accurately a point of no return. Theoretically, the decision-making process to reject the takeoff must be made prior to reaching the V1 point. According to FAA rules, V1 is defined as the speed at which an engine failure has been recognized and action initiated to either continue or stop the takeoff. The time to begin the decision-making process, therefore, is not at or near V1. A balanced field length theoretically exists when the distance needed to accelerate to V1 and then stop is equal to the distance needed to accelerate to V1, experience an engine failure, and still attain a height of 35 feet. In other words, if the pilot recognizes an engine failure at or above V1, he will have enough performance to continue the takeoff. Using the proper technique, he is assured of attaining the FAA required height of 35 feet. A balanced field length also means that if a pilot recognizes an engine failure and simultaneously begins to retard the throttle and apply the brakes at or below V1, he can stop on the runway. But how is the stopping distance determined? On the DC-10, it was determined based on retarding throttles to idle, manually extending the spoilers, and applying maximum braking on a dry runway within 2.2 seconds of engine failure. To this, the FAA adds 2 seconds with no deceleration. The FAA calculations include 1 second to retard throttles and 1 second to deploy spoilers. Flight test stopping distances for the FAA certified performance charts are obtained using actual flight procedures and flight test data. To calculate the stopping distance, it is assumed that an engine failure occurs just prior to V1. This means that the pilot's recognition and decision to abort coincide with the V1 speed. The demonstrated recognition and initial action time varies for every aircraft. For the DC-10, it's about 1.1 seconds. For the Boeing 747, it's about 1.2 seconds. Next, the time required to initiate brake application, move the throttles to idle, and manually deploy the spoilers is measured. The FAA then adds a 2-second delay to this time in order to calculate the stopping distance. This footage of a successful emergency stop was taken during the flight test program. It clearly shows what happens when millions of foot-pounds of energy are dissipated by conversion into heat. The aircraft is certified if the fire doesn't spread to the aircraft or its structure within 5 minutes with no fire suppressant applied. We've now seen how the aircraft is expected to work during a rejected takeoff. But we've also seen what happens to the aircraft when you make that high-energy stop.
We mentioned before that you won't want to abort if you have a tire failure. If there are any absolutes about rejecting a takeoff, this is as close as you'll get. By virtue of the way this aircraft is certified and the way these calculations are made, you won't be able to stop on the runway. Instead, you should take off, dump fuel, and assess the damage with a tower flyby. But there are more than tire failures that will affect your stopping performance.
It's important to note that FAA performance charts are based on stopping on a smooth, dry, hard-surfaced runway. In addition, aircraft are demonstrated to the FAA with new tires and new brakes. However, no credit is given for reverse thrust. In other words, in an actual RTO situation, using reverse thrust enables an aircraft to stop shorter than the predicted FAA distance. In actual practice, however, a 1 or 2 second delay in initiating an abort can eliminate any advantage the use of reverse thrust provides. In addition, aircraft may operate with one or more of the following: worn tires, hot brakes, and worn brakes. Obviously, a hot brake is not capable of dissipating as much heat as a cool one. Heat buildup can be caused by riding the brakes to control taxi speed or making short turnoffs after landing. To improve stopping capability, both practices should be avoided. Failure to use all the available runway, particularly if you're a heavy and field length critical, decreases your available stopping distance. The FAA-approved flight manual does not include line-up distance in RTO stopping distance calculations. So let's say your company does not factor line-up distance in your takeoff performance. Consequently, if your main gear is 300 feet from the end of the runway when you start rolling, you've already lost 300 feet of stopping distance even before you release the brakes. Stopping distance is also reduced if you start rolling slightly before application of takeoff power. Power should be set by 80 knots. It's important to reach this speed as soon as possible to conserve the precious real estate that may be needed for an aborted takeoff. The runway slope is another factor affecting stopping distance and is taken into consideration in stopping distance calculations. However, the fact that a slope may go up, then down, is not necessarily taken into consideration. On the uphill portion, you're not accelerating as fast as the book value. Conversely, when going downhill, you're not stopping as fast. Other factors such as weather, wet runway, inoperative systems or equipment, and crew fatigue can also work against coming to full stop before the end of the runway. Therefore, good judgment may suggest establishing the lowest V1 speed to provide an additional margin for stopping in the event of a rejected takeoff. Takeoff speeds can be varied by changing the takeoff flap position or by using the unbalanced runway concept. This concept determines the lowest V1 from which the aircraft will still accelerate to VR with the critical engine failed, then lift off and reach V2 speed at 35 feet above the end of the runway. This chart compares the penalties on both sides of the RTO decision equation. The negative values of speed refer to those speeds below V1. The positive speeds are those above V1. The left side of the chart shows the height attained above the end of the runway for a 3-engined aircraft if the takeoff is continued with an engine failure before V1. The right side shows the speed the aircraft will go off the runway for the various abort decision speeds above V1. As you can see, the penalties associated with aborting the takeoff at a speed above V1 are far more severe than those associated with continuing the takeoff with an engine failure before V1. This is not to say that you should continue the takeoff if you lose an engine before reaching V1 on a balanced field. This chart is simply a comparison of the performance penalties between rejecting the takeoff above V1 with all engines operating and continuing the takeoff with one engine failed before reaching V1. By now, you should have a little more information on which to base your decision. Do you abort the takeoff or go? We've seen that the decision to abort can result in dire consequences. We've also seen that many takeoffs that were rejected were done so unnecessarily. Often it would have been better to go and sort out the problem in the air. We've also taken a look at how aircraft are certified and seen what happens to the aircraft when a takeoff is aborted at maximum energy conditions. Finally, we've learned that there are factors working against making a successful stop on the runway.
Nevertheless, there will be times when a rejected takeoff is the only reasonable decision to make. How can we better prepare for that moment? As we mentioned earlier, experience and the RTO simulation program have taught us that the pre-takeoff briefing must include the possibility of a rejected takeoff.
V1 is 154, VR 162, V2 168, flap retract 173, slat retract 216, and a zero retract min-maneuvering 250. If we have an emergency prior to V1, I'll command abort.
Through a series of simulations, we've also learned that on first runs, most pilots do not achieve full anti-skid braking in time, come out of reverse early, and tend to let up on the brakes as speed decreases. Therefore, they achieve less than maximum deceleration. Also, significantly, in the majority of overrun incidents, the pilot felt he'd had it made when he did not. Remember, maximum deceleration capability of the aircraft can only be obtained from full brake pedal application.
In subsequent simulations, however, the pilots employed improved techniques and stopped on the runway. Simulations like this, as well as a new McDonnell Douglas blown tire simulation program, can only help prepare you for the moment of decision.
Obviously, once the decision has been made, the pilot must follow the proper abort procedures. He must rapidly retard throttles to idle while simultaneously applying maximum brakes, then select reverse thrust. Check to see that the auto spoilers have deployed, and if not, deploy them manually. Apply full reverse thrust as soon as possible. Apply just enough forward pressure on the yoke to keep the nose gear on the runway, and maintain full brake pedal deflection and maximum reverse thrust until the aircraft has come to a full stop. Too much nose-down elevator tends to reduce the downward force on the main gear, thus reducing stopping capability of the brakes.
Systems are currently under development and being employed on aircraft such as the MD-11 to lessen the ramifications of a high-energy abort.
The auto brake system available on the DC-10 and standard equipment on the MD-11 will automatically apply the brakes the moment a rejected takeoff is initiated. When the spoilers are armed, they will automatically deploy when a takeoff is aborted. Standard equipment on the MD-11 includes a brake temperature monitoring system. This system alerts the flight crew when a brake is hot and displays malfunctions on a system display screen. Brake temperature sensors continuously monitor the brakes and alert the flight crew when a brake temperature rises above a preset level. This abnormal brake temperature will be highlighted on the display. Also standard on the MD-11 is a tire pressure indicating system. Whenever any of the tire pressures fall below a set level or change a set amount from a paired tire, the crew receives a low tire and master caution warning. If any tire drops below 50 psi, a voice alarm calls out tire failure. The MD-11 features double overload tires as standard equipment. If any one tire fails, its mating tire on the same axle will support the load without failing. The MD-11 has new carbon brakes which have longer brake life than comparable steel brakes. The aircraft also includes a new digital-controlled anti-skid system that automatically tests itself for proper functioning when the gear is lowered. Finally, to minimize the possibility of an RTO due to a false warning, portions of the MD-11 crew alerting system that are not critical to takeoff are inhibited. Both aural and visual warning lights are inhibited from about 80 knots to V1 up until the aircraft reaches 400 feet altitude after takeoff.
By now it should be obvious that a rejected takeoff is one of the most demanding maneuvers that a flight crew can perform, especially if performed at or near V1 in a runway-limited situation. Although a high-energy abort is not a common occurrence, it does happen. And when it does, nothing less than a split-second decision will do. After all, at 180 knots, each second of delay will propel you another 300 feet down the runway, the length of a football field. However, with an awareness of the ramifications of a high-energy abort, a knowledge of aircraft performance, and an understanding of the proper abort procedures, you will be far better prepared for your own moment of decision.